Hello everyone, this is Dilip. Today let's take a look at implementing support vector missions using Python and Sci-kit Learn. We'll also see under various scenarios whether to use support vector missions or neural networks. So in the last video, we spoke about linear and nonlinear kernels in SVM. We have already seen about the Gaussian kernel in the last video. So this slide tells you when to use a linear kernel versus nonlinear kernel. So this is taken from this source. So I put the source also as well here. So if n is large, means if we have a large feature set, but m is small, but training data is small. So then we can either use logistic regression or SVM with linear kernel. So both of these have similar complexity. And in some cases, SVM with linear kernel gives better result. In some cases, logistic regression gives better result. You can try both and pick one. So if n is small, say number of features is within the range of 1000 and m is intermediate. So we have a large training samples, or you can call it intermediate since it's only till 10,000. Then you can use SVM with Gaussian kernel or polynomial kernel. So we need a better nonlinear kernel because the feature size is small. And if n is small and m is very large, say 50,000 to 1 lakh plus training samples you have, but you have only 1000 features per training sample. In that case, what we have to do is either you can go with neural networks, or if you want to use SVM and logistic regression, one of them, then we need to manually add more features and then use logistic regression or SVM with linear kernel. So this manually adding more features for a large training sample, this is one of the reasons why neural networks is preferred over SVM for training large data sets. So let's move on. So we'll use the same MNIST data set which we used for coding the neural networks from scratch using Python. So you can check out the playlist if you have time for that video. So here we'll use the same MNIST data set where there are handwritten digits from 0 to 9, and we have to recognize them, whether they belong, whether it is 1, 2, 3, or whatever it belongs to. So we have 10 classes since we have 10 digits from 0 to 9 to classify the given input data. So each handwritten digit you see, it's a 28 cross 28 image, which is given as a input to us. So for this, we'll use Sci-kit Learn. So Sci-kit Learn is a free open source machine learning library. So it's not tied to any company like, say, Google's TensorFlow or Meta's PyTorch. So this is like a open source machine learning library. So even those are open source, but this is much more like it's not tied to any company, and it's easy to use interface and code. So I'll just show you how we'll put the SVM using the Sci-kit Learn. You can see how easy it will be, and although it is written mainly in other languages like C++ or Java, so it's better to use it with Python because it is optimized for Python. Okay, let's go to the coding. So we'll just initially use the TensorFlow to download the MNIST dataset because it's easier that way. And this is okay. This function will come back later. So okay, let's ignore that. So we're just downloading the MNIST dataset, and then we are splitting the data between train and test set. So approximately it will split the training and test data. Like it will make 60,000 training images and 10,000 it will put in the test images. And white train is the classification. So whether it belongs to first class or second class, third class, fourth class. And white test is the testing classes. And then we do the normalization. So since the pixel values between 0 and 255, and you want the values to be between 0 and 1 for better machine learning uh, hypothesis and cost function optimizations. So we just divide everything with 255.0. So make sure we get a floating point value. So now we have the normalized training data and test data available here. So this just shows the output. So it is downloading the data, and the length of the training data is 60,000 it shows. And then we are reshaping the data. So what happens is, whatever the test data you get, say training data, you have 60,000 training samples, and each training sample is a 28 cross 28 image. Okay. But for scikit-learn API to pass into that API, what you need to have is, you need to have a uh, one-dimensional array indicating all the features. So per test sample, say, but since we have 28 cross 28 images, to make the 2D into 1D, what we do is we just reshape that such that the 28 by 28 is 784. So all the 784 features will come in one single array. And then anyway, we'll prepend the, uh, so there will be like one more array, uh, which will have the sample number. Okay. So right now our training data will be like 60,000 training samples, 28 cross 28. So it's like a full 3D. So to convert this 3D, 3D, 2D, what we do is we do reshape, and then we give it -1 comma 784. So what it will do is, it will make it a 60,000 cross 784. So initially this is 60,000 cross 28 cross 28. Okay. So uh, so what happens is, if you don't know the size of the training data, we can just put -1 here. It'll automatically make it, or you can give reshape 60,000 comma 784. It is the same result it will give. And we're just printing the new shape. We are also checking the size of the chart. What are the results in the training data? Since we have 60,000 images, 60,000 is the size of the output classes. Not output classes, but size of the complete output class. So there will be like one digit, whether between 0 to 9, what will be stored in this 60,000 1D array. Okay. So after we do that, then it's simple calling the scikit-learn svm API. So we just do svm.svc. We put kernel equal to RBF. So in the last video, I've already shown this kernel, how it looks like. It's e to the power of distance between the vector and the existing features, like input features, divided by 2 sigma square. So that is the RBF kernel, or we can call it Gaussian kernel as well. So we just call it once. So we just initialize SVC with the kernel as RBF, and then we call just fit whatever the reshape training vector we have done and the results of the training data. So if running of this scale-up.fit, if it outputs SVC, it means it has completed training. So training for the 60,000 training samples, I have seen it takes 4 minutes. So I have already run this just before the making of this video. So you can see it's 4 minutes mentioned here. And okay. And one more thing is, using the RBF kernel, why I use the RBF kernel? Why I use nonlinear kernel is because the number of features, it is like very small. So per sample, we have 784 features, but the number of training samples is huge, like 60,000 training samples we have. So this makes us go to the so we'll see the presentation again. So this makes us go to the third feature. So if n is small and m is large, 50,000 to 1 lakh or 10 lakh training samples you have, then we need to manually add more features. Okay. So instead of adding more features, I'm going with the Gaussian kernel. And from my observation, so after clf.fit, we can do this score also over the test data. So we'll reshape the test data as well, and I have taken the score, which will give me the accuracy percentage. So I'm getting 97.9%. And with linear kernel, I was getting 91% accuracy. But with Gaussian kernel or RBF kernel, so both are same Gaussian or RBF. So with that, I am getting 97.9% accuracy. And both are taking 4 minutes for training. So even though training set is huge, both are taking only 4 minutes to train. This is because most of the SVM libraries, these are like optimized. And Sci-kit especially uses already the optimized SVM libraries. So that's why we are able to train also much faster. So after we have trained, we can try to predict. So here I'm trying to see what are the fifth test sample. I'm just asking it to predict, and I'm also printing it. So it has predicted 1. This is the value of 1. So let's just see seventh test sample. So it has predicted it to be 9. And this is also 9. So let's look at number 8. What is the 8th test sample? So 8th test sample is, oh, this looks different. Yeah, but it has predicted it to be 6. Let's see what is the actual value of it. Okay, so this is 5. So you can see like it mispredicted this one, but I don't think we humans also can predict this to be 5. Okay, so let's just print out the 9th testing sample. Okay, so this is 9. Actual result is also 9, and the prediction is also correct. Okay, so I'm just predicting and checking whether for so human verification kind of. I'm just checking if it's actually giving the correct result. So the CLF.score, we can use it to predict the accuracy percentage of the SVM. So all this CLF, what I'm using this, so this is exclusively part of Sci-kit Learn library. And you can see with only 2 or 3 lines of code, I was able to fit the SVM, and I'm able to predict as well. Okay, so whenever you are using for SVM, if you want to use, better to stick with Sci-kit Learn library. And in TensorFlow, I have searched a lot. There is no usable interface for SVM. Even I think in latest TensorFlow, they completely removed the SVM, I believe. So do put in the comment if that's not the case, but I checked extensively, it's not there. So in TensorFlow 1.0, and then it used to be the experimental library, something used to be there. But now that whole experimental APIs, they have removed. So the modules, whatever are there, they have removed. Google has removed them. So I think in latest TensorFlow, there is no support for SVM at all. And they're asking to use neural networks only. And they are also, they have example showing a quasi SVM using the neural networks. So that and all is a topic for another day. Let's ignore it. But for SVM, if you want to use, go with the Scikit Learn library. And yeah, so here I'm using the TensorFlow. So TensorFlow, using a TensorFlow API, it's very easy to create the neural networks. You have seen my neural networks from scratch video in my playlist. If you have, just check it out. You can see that how much code I have written for coding the neural networks, and it was running slow as well. But TensorFlow, it's optimized for neural networks. So if you want to use neural networks, better go with TensorFlow. So this is a simple thing. So keras.model sequential. What I'm doing is input whatever is coming. I'm just doing a flatten. Okay. So flatten in the sense it will just make it whatever the reshape we are doing, right? Same thing it will do. It will make it a 1D array. So this is the first layer. So the first layer size is equal to the input features. Now that's always the case with neural networks. And in the hidden layer, we are taking 128 neurons, and activation function we are taking as ReLU. And in the third layer, we are taking 10 neurons because there are 10 classes between 0 to 9 digits we have to classify. And we are using the activation function softmax. So just your neural networks is constructed. So, and then you need to compile the neural networks. So this is optimizer. So optimizer, you want to use gradient descent or Adam. So good advantages about this is Adam will help in faster convergence. So generally these days we are going with Adam most of the time. And loss is sparse categorical cross entropy. So for images, this works well. When I'm not sure what does it do. And metrics equal to accuracy. So this is like whatever the accuracy metric I'm getting, I want to use it. So just I put metrics equal to accuracy. So it will display also when running the code. So I remember the initial function I was talking about. So here what I'm doing is, so once I reach a 99% accuracy, I'm asking it to stop the training. So this is a class of the keras callback, which I'm inheriting. And once on epoch end, so any training iteration ends, I'm just checking the accuracy. If it's greater than 99, I'm stopping the training. Okay. So yeah, this runs very fast. I can run it now itself. So what it is doing also I'll tell. So it is taking 1875 samples and it is training over them. And you can see accuracy improving in every step. Initially, first iteration, it was like 92%, 90%, 97%, 98%. I think by fifth iteration, it might reach 99. Yeah, but it did not. Maybe we should have run more iterations. And you can see the accuracy level. So it is like 97% accurate with the test data. So it is tested using only 13 samples, but it's a 97% accuracy. So I'm also just for human confirmation. I just taking one random training test sample and just for the first test sample is there and just printing out the data, printing out the image as well as whatever it classified. So it classified it properly. Is the prediction. Okay, so as you can see, so this is a neural network output of all the neurons. And if you see all these values, this value is the lowest. So it means this is a result it is predicting. So there is 0, 0th error. These are all output neurons, right? So this is 0th, this is 1, and this is the 2. So it belongs to number 2. So even our whatever the printed the test data, original result is also 2. And the image is also 2. So yeah, just for human, like just for our satisfaction, we do this. But usually this, whatever the accuracy it gives here in the test samples, in the model.evaluate function, that is the correct accuracy only. So what we learn from here? So even though with less number of training samples, so you can see per epoch, it has used 1800 training samples. So 1800 into 5, I think nearly around 90. So it's around nearly 10,000 training samples. And with 10,000 training samples and randomly selecting the training data, we can get a good level of accuracy with neural networks as well. So if we have less number of features and more training samples, okay, so you can see the accuracy levels of SVM trained over 67 training samples and accuracy level of neural network with 10,000 training samples, it is the same. Okay. So why I am raising this point? Let's go back to the slides. I'll just show you. For large data sets, neural networks takes more time to train, but SVM is faster to train. You have seen like within 4 minutes, it was able to train the full SVM. So SVM is faster to train compared to neural networks. But we can offset this by taking a smaller set of training data and randomly picking up. So even with 10,000 samples, we have seen neural networks performs same as SVM with 60,000 images. So if we have a small set of features and large set of training data, better to go with neural networks only. But if we have large set of input features, large set of input features, I would say in natural language processing. So where we have a lot of English vocabulary. So in those cases, SVM makes sense, but in all other cases, neural networks makes more sense, because for SVM to train, you need to manually extract more features, and manually extracting features is error prone and not good. But with neural networks, even with less number of features, if you have sufficiently large training data, you can get always good result. So that is a precondition. You need to look at it whether to go with SVM or neural networks. But if you have a large set of features and small set of training data, it is obvious to go with SVM. So thanks everyone for watching the video. Please like, share, and subscribe. Thank you.